Welcome everyone. It's a pleasure to have David Kosower for his third lecture on loop level technology.
Thanks. I see some people have used the opportunity to escape, but I hope they come back. Actually, before I begin, I wanted to mention one thing, which even to people in the field is not so well known, that this amplitude is of course related to the original Park-Taylor amplitude, but it really should be called the Nair Park-Taylor amplitude. And Nair is Parameshwan Nair, who's a professor at City College in New York, and he's a very quiet guy, very original guy, and he's actually, first of all, responsible for writing down the original form of this, and also for some of the early insights that ultimately led to twistor strings and indirectly to the DCFW formula that you saw earlier. And he's a fellow I worked with earlier when I was a young postdoc, and someone who doesn't really get quite enough credit for the things he's done. So I thought I would like to mention that at the beginning of the lecture. So we're going to pick up where we left off yesterday, but since there was a little bit of confusion, I think, among some people, I thought I would take a few minutes to kind of start again with the box integral and just quickly do the highlights of the global pole and global residue. So we had started with ignoring a little bit the issue of infrared divergences and writing down the box integral. And the situation we ultimately were looking at was where the first and fourth legs were taken to be massless. The others might be massless or massive. And we followed the naive, initially we followed the naive Kutkowski procedure of cutting, in the Kutkowski sense, these propagators, giving us the delta functions and that is telling us that we have to solve the simultaneous equations that correspond to them. So we're trying to localize the integral on the simultaneous solution of these equations. We also saw that we can write down those solutions explicitly in terms of spinors. So let's write down A, and so we have 1/2 plus 1/2 or 1, 2, 4 times 1, 4, and of course the spinor conjugate of that expression also a solution. So 4 spinor chain 4, 2, 1, and then 4 mu 1 in the numerator. And these are generically complex vectors. So if we're doing a real delta function integral, we'll simply get 0. It's not incorrect, but it gives us a useless equation. 0 equals 0. Very hard to solve that for unknown coefficients. So instead we introduced a kind of generalized delta function, which is determined by, so in a single variable, it's given by contour integration. So we're we're going to define it to be an integral around a contour that surrounds the root of the delta function, surrounds the solution of the delta function. Again, this is assuming that this is a simple pole. You can generalize it in other cases. Now, of course, if you follow the kind of the story of Humpty Dumpty, the children's tale, then you could imagine making words mean whatever you like. So you could imagine making the symbol mean whatever you like. But in fact, it's not, even though it's written in terms of coloring, it's really trying to do the same thing. This is trying to fix the value of z to be the root of this equation. And of course, this integral is also essentially going to extract the value of this polynomial at the solution of this equation. So they're really morally doing the same thing. It's just that this generalizes into the complex plane, into complex solutions from things that were purely real. So in our context, we are doing this in 4 dimensions. So we're taking the integral over d4L, which started out as an integral over 4 real components. That's the idea. We're not integrating over all complex components. And we generalize that from Minkowski space or to c to 4. And of course, our original integral now is still just taken over the Minkowski slice of c to the 4. So what we're going to do in order to get this contour is we're going to replace the original contour by a contour that encircles these 2 solutions. And that contour in this case is just going to be a 4 torus. Or actually they're going to be, as we'll see in a second, there are 2 different 4 tori. And the thing that I want to emphasize is that, of course, we all know how to do contour integrals, and we kind of shift the contours around in order to do these integrals. This is not what we're doing here. We're not trying to keep the value of the integral the same and just manipulate the contour to make it easier to do. We're really replacing the contour. And that's taking the original integral and it's replacing it ultimately by something called its global residue. And that's the generalization of cutting as a means of analyzing the analytic structure of the function. This is a different kind, a different tool that we can use to analyze the analytic structure of the function. Of course, the function on both sides of our master equation has to be the same. So whatever analytic structure we look at, whatever properties we look at have to be the same. And we're going to pick out those properties that help us get simple equations for the solutions, the coefficients. So this is actually an opening to a very interesting topic, which I'm not going to say anything more about really in this series. The multivariate complex analysis, multivariate complex integration is a much more complicated subject than single variable ones. And there's much less kind of detailed, computationally oriented mathematics in the literature than for single variable complex analysis. And partially it's because the subject is more complicated and a little bit more obscure, and partially because sometime in the early 20th century, mathematicians stopped calculating and decided the only interesting thing to do was to prove theorems. Of course, as physicists, we need to keep calculating, so we can't let them stop us. Okay, so, whoops, I should move that up a little bit further. So, you've noticed there's a problem here that, actually there's 2 problems, one of which is probably obvious, the other which is not so obvious. So the first problem is that we have 2 contours. The question is, which one should we choose? And the other problem, which is not so obvious, is that we derived our master formula, and we implicitly relied on certain properties of Feynman methods. And one of the properties we relied on is parity. So we relied on the fact that this integral with a Levi-Civita symbol in the numerator is 0. So of course, if you go through a derivation and you rely on a certain property and then you obtain a certain final formula, you'd better make sure that whatever manipulations you do respect that assumption, respect that property. Otherwise, your final formula is not justified. And in fact, if you, this is true, but it's true only if you're integrating on the real slice. And now we're going and replacing that real slice with some contour that's way off in the complex plane. We can actually draw a little picture here. Find the right color chalk. So imagine that it's kind of hard for me to draw the four-dimensional complex space on the blackboard. It's hard to manage really anything more than projecting 3 dimensions. So I'm going to draw one component, and this is the complex plane. So we know that there are various poles right next to the real axis from the I epsilon prescription. And our original contour was just running along the real slice. Now we've gone and we've replaced it. This is not a contour deformation. We've done a contour replacement. So we have the poles here are still sitting wherever they were. But now we have some solutions which are way off in the complex plane. And actually I should draw them in a certain sense. So conjugates, although whether they're exact conjugates or not depends on the signs of the energies. And if we were to do the integration around just one of these contours, then this equation would no longer hold. So our entire derivation, or at least the last part of the derivation, when we went down from general 4-point functions to scalars, would not be justified. So one of the amazing things that happens here is that these two problems essentially cancel each other out. So what we're going to do is we're going to pick our contour, a linear combination of contours. Imagine that we choose some contour that's a linear combination of contour 1 and contour 2. Again, you should think of this as kind of a one-dimensional slice. It's really a 4 torus, and I've sliced it and suppressed some of the dimensions. So imagine we have some general contour here, and we try to integrate this function on that contour. Then, roughly speaking, we're going to get something like this. We have an epsilon symbol, and we have our denominator. And of course, we change variables to match the coordinates of our 4 torus. And now we require that this is equal to 0. And if you work this out, you find that that requires that for an appropriate convention on the orientations of the contour, that these two coefficients be equal. So in other words, we're going to enforce this condition that the integral of epsilon be vanishing even on this complex contour, and that will pick out a unique contour for us. So that tells us that we have to sum over the two solutions that we have with equal weight. And this kind of philosophy you can actually go on and apply at higher loops, and you don't always get such a simple constraint, but there are constraints that you get from it. So if we go back to our master formula, so remember we had a master formula that said the amplitude is sum over our basis, which consisted of boxes, triangles, and bubbles, plus a rational term. So if we now take our quadruple cut in this more sophisticated version, and we apply it to both sides of the equation, well, everything but a single box is going to disappear, because there's only going to be one box that has these particular four propagators. Yes?
This condition just fixes the coefficients up to an overall
That's
factor.
correct. That's correct.
But it doesn't matter in the end.
Just patience. I have not forgotten the overall factor A. Yes, so there's an overall factor A. What about it? So, because, for example, the triangle simply will not have a quadruple cut. If you're looking at, for example, a different configuration of the external masses, let's suppose that legs 2 and 3 are both massive, so they're each as a sum of momenta. You move one of the momenta from leg 3 to leg 2, that's going to change the locations of these two poles, and now you try and do a contour integral around a place where the integrand has no pole, and you just get 0. You don't get anything interesting. And as the contour shrinks, phases cancel, and you get nothing. So this is going to pick out a single integral, and of course the rational terms are also going to go away. And so on the right-hand side, well, what are we going to get? We're going to get our particular coefficient, let me call it CR. When we do a contour integral, then depending, for example, in this simple one-dimensional case on the coefficient in front of z, there's going to be some Jacobian. And as you remember from yesterday, that Jacobian just appears without an absolute value sign. It's just 1 over the derivative of the second polynomial at the pole. So there's some Jacobian. And in fact, there's also this factor A. There's the overall normalization of the contour, if you like. If you want to think of it as some integer, the number of times that we decide to wind around the contour. We can decide to do the circle once, but we could also decide to do it 17 times, or 3.5 times. Why not? So there's the factor A. And then here in the integral, that's it. I mean, the residue, if I now go back to the original integral, I just have 1 here. That function in the numerator, the polynomial 1, is just 1. So I just get it, I'm summing over the two solutions, so I'm just going to get the number, I'm just going to be times the number of solutions. So the Jacobian, we could actually calculate if we cared about it. The only thing that's unknown here is, genuinely unknown, is our coefficient. This is the object that we are trying to determine. Okay, so what about the left-hand side? Well, the left-hand side is going to fix the value of the loop momentum. So this global pole, this generalized unitarity operation, generalized cutting operation, is going to fix the value of the loop momentum to one of those two values. Those are on-shell values. And so on the left-hand side, it's going to replace those specific propagators by on-shell momenta. So what are we going to get on the left-hand side? Well, we're going to have a sum over the different solutions. So this is solutions, the A and B for the loop momentum. And of course, they're massless momenta, so we can easily find spinors that correspond to these momenta. So if we need spinors at some point in the calculation, we have solutions for the spinors as well. Now we know at loop level, of course, we can have different particles circulating around the loop. So there could be gluons, or there could be quarks, or maybe other things if we're thinking about general theories that have nothing to do with the real world. So there's going to be some sum over the internal species. And of course, there's also the sums over the helicities of the internal lines. And what's going to be there? Well, maybe we should draw the diagram first. So we have four corners of our box. My very limited design skills are suitable enough to get you a clean picture here. Okay, that's, well, it's a circle with indigestion, but anyway, it's supposed to be a one loop. And we've imposed this generalized cut, which replaces those propagators by on-shell momenta. And we, in general, have a whole bunch of legs sticking out of each of these vertices. This could be one, or it could be many. So what we're going to get here are just four different tree amplitudes. So this object here, these lines, of course, are all physical and on-shell, and these lines are now going to be put on shell by the generalized cutting operation. So this is a tree amplitude, and then each of the corners has a different tree amplitude. So we can not use that chalk. So we have a product of four tree amplitudes. And of course, unlike the integral itself, these amplitudes are functions of the momenta. They're non-trivial functions of whatever the momenta or the spinors are of these various legs. So we have to evaluate them at the solution. Let me label these S. Okay, well, we've done an integral on this generalized contour integral on the left-hand side. So whatever the Jacobian we got over there, we still have over here. So this is Jacobian. And in addition, if we decided to wrap around the contour, once or 3.5 times or 10 times, we have to count that as well. We get that number of copies of the solution, so we have our factor A here as well. Now, these two things are equal. We're going to set them equal. Again, for the purposes of this lecture series, I'm going to assume that you've all understood and practiced the VCFW recursion, so that if I ask you for some tree amplitude, it doesn't matter how many legs and exactly what the legs are. If you know the theory that, let's say, it's Yang-Mills theory, let's say with everything in the adjoint, just to make life simple, so n equals 1 supersymmetric Yang-Mills, I give you an arbitrary tree amplitude, and then in some amount of time ranging from 5 minutes to 5 days, you come back with an answer. So everything on the right-hand side, in principle, is known, or you know how to do it. And again, the Jacobian, of course, is the same Jacobian, so we can calculate if we want. A is just something that we impose by hand. So now we're going to set these two sides equal. And that gives us an explicit formula for our coefficient. In terms of a certain sum over tree amplitude. So our desired coefficient is going to be equal to 1/2, which is dividing out the number of solutions. We have to sum over the solutions, which I'll label by S. We have to sum over the species and over the helicities of the lines running around the cut loop. We have, I'm just going to copy over this formula. Give you a chance to catch your breath and maybe write it down yourselves if you didn't manage to do it the first time around. And of course, the factors of A and the Jacobian drop out because they're common to both sides of the equation. So, in fact, there's no particular reason to do anything more than wrap around the contour once. So this formula is originally due to to Brito, Chazo, and Feng. And it has a number of really neat properties. So first of all, it tells you the coefficient, the rational coefficient, in this case of a box integral, purely in terms of on-shell tree amplitudes. Of course, what makes this magic possible is that the cut lines here, that those lines in the tree amplitudes are with complex momenta. So again, complex momenta entering everywhere. We didn't need to do all these algebraic reductions, all the reductions of integrals, all the tensor reductions, because it's all kind of incorporated into the formalism. We just needed to keep in mind that it's all been done, because when we're applying these analytic analysis tools like the generalized cutting, there's assumptions about what the right-hand side looked like. And so we have to know something about what reductions were done, but we only need to know them in the abstract. We don't need to know them explicitly. The other thing that's kind of neat, and wasn't maybe really touched on by Professor Hen, is that this is a formula that you can evaluate purely numerically. You never actually need to evaluate anything analytically if you don't want to. It turns out BCFW is not the ideal technology for doing things purely numerically, although it can be done. But however, whatever means you choose to evaluate the tree amplitudes numerically, and there are things like the Behrens-Hiller recursions as well as BCFW, then with that you can run this calculation purely numerically. So you never actually have to write down very complicated analytic formulas and program them in. You can do everything essentially recursively in a purely numerical form. And that's in fact how a lot of the codes that implement this at one loop work. Now, I don't know that I'm going to go through the triangle coefficient in a lot of detail, but in any event, before we talk about the other integrals, then I think I'd like to do an example. Before I do the example, though, I'll stop and ask, are there any questions? So if I pick a random person and quiz him or her, then we'll be able to reproduce this derivation? All right. Okay, if you have any questions, of course, stop me. So let's do an example, and we're going to compute, we're going to look at the 5-point amplitude. Yes?
Yes, when you think of the left-hand side, then you don't really think of it as a function of your variables because you have changed the contour. You really think of it as the sum of Feynman diagrams then. And
okay, so if you want to, I think that again, whenever you're doing the analysis here, it's true that we're peaking inside the Feynman integrals. So you do want to be thinking at this stage of the left-hand side as an integral over some integrand. But that integrand did not have to be produced from Feynman diagrams. From a Gedanken point of view, from just kind of an abstract point of view, just as an organizational tool, you can certainly start by thinking of the left-hand side of amplitude as being the sum of all the one-loop Feynman diagrams. And then I'm going to identify all the diagrams that have the 4 propagators that I want. I'm going to cut those propagators in precisely the sense of this global pole. And then I'm going to do the sums, that decouples the sums on the different 4 corners. I can resum those sums, and I know I have an amplitude. So I never actually have to compute a Feynman diagram, but I can use it as a mental tool to understand the objects that I'm computing. I hope that answers the question, maybe clarifies something for people. Okay, so we're going to look at, in fact, one of the simpler generalizations of the Parse-Taylor amplitude. We're going to compute a certain coefficient in the one-loop amplitude with the following external helicity configuration. So it's a 5-point amplitude. And it's convenient here to draw a diagram, but let's go ahead and compute a certain integral. So in fact, the coefficient of the integral where k12 is the first argument and the other arguments are 3, 4, and 5. So let's see, I want to keep the picture. So let me move this over here. So we're going to look at one particular box in this amplitude. So let's draw it out nice and big. So that's 1, 2, 3, 4, and 5. Let me label the helicities. So 1 minus, 2 minus, 3 plus, 4 plus, and 5 plus. So, and of course we've imposed the cutting procedures. So we've split this up into 4 tree amplitudes. These are on-shell tree amplitudes. And we have to sum over helicities. So we're going to have a variety of helicities here. Let me call this one sigma 2. And again, we have the convention at each of the corners, all the momenta are directed outwards. That means that the momentum here is directed this way, here it's directed that way. So when we flip the sign of the momentum, we flip the sign of the helicity. So that's why it's sigma 2 and minus sigma 2. That's what helicity conservation means. And we call this one minus sigma 1 and sigma 1. Now, we've already seen in Professor Hen's lectures what is allowed for the vertex in the lower left-hand corner. So for example, you might think I need to sum over, there's a total of 4 cuts, each one can have 2 helicities, I should need to sum over 16 different terms. But in fact, if I were to put, for example, a plus and a minus here, what do I get for the lower left-hand corner? Yes. Why do I get 0? Yes. And likewise, if I were to put in 2 minuses, then also I'm going to get 0. So in fact, there's only one choice that's left here, so I won't even bother to write down sigma 3 and write it down. I'm starting with the plus. And that, of course, is going to then fix the helicities over here to be minus and minus, but we now need to go through an analysis of what helicities are possible for sigma 1 and sigma 2. So let's draw a little table, sigma 1 and sigma 2. And they're going to be 4 different options. They can both be minus, they can be minus and a plus and a minus, and finally a plus and a plus. Okay. So let's start with the simplest one, which is the minus minus. So let's look at the upper right-hand corner of our integral. So it's minus sigma 2 and minus sigma 1. So in that case, that would mean that we'd have a plus and a plus. And that thing, at least in pure Yang-Mills, is going to be 0, because there is no 3-point all plus amplitude. If you introduced an f-cubed operator, as some higher dimension operator, you would get such a thing, and be made possible by the fact you have a dimensionful coupling that can then make the dimensions of the corresponding 3-point amplitude correct. In fact, that would be, I should maybe leave that as an exercise. What 3-point amplitude do you get from introducing a G-cubed, trace G-cubed operator? So imagine you have your Lagrangian, which is just the standard Yang-Mills Lagrangian, and now you put in a trace G cubed operator. So G here is being the field strength, right? The commutator of du and du. Okay, but in any event, we haven't introduced such a thing, so this we're just going to get 0. Okay, let's go on to the next situation where we take sigma 2 to be plus. So then we have, let's draw, what color should I draw? Let's draw it in orange. So we have a plus here, and then this, of course, is a minus. And then we're choosing sigma 1 still to be a minus, so this is a plus. And well, this would be minus, but let's not worry about that for a moment. So then we have a plus plus minus vertex over here. We have a plus plus minus vertex over here. And at least naively, everything is happy. Those two are both non-vanishing. So just to see who's awake, is that a vertex with brackets, or is that a vertex with angles? Plus plus minus, which of the vertices is that? Yes. Okay, so what does that mean? If it's a bracket vertex, well, the only way we could solve the kinematics at 3 point is to have the lambda spinors, that is the angle spinors, all be proportional. So we have some cut loop momentum here, and let me actually label these now. So I'll call this one L1, this one L3, L4, and L5. For those of you who are wondering why I'm discriminating against L2, it's because it got sucked up here in between particles 1 and 2. So I can look at, so I know that the lambda spinors for that vertex all have to be proportional. So that's the way I solve the on-shell conditions.